All right, we're going to take a look at 10.5, solid states of matter. We've seen gases, no intermolecular forces whatsoever. We've talked about liquids and their changes in property because of intermolecular forces. And then we're going to look at solid state, which is even more important to look at intermolecular forces. But we're more going to look at the structures. We're going to kind of avoid talking about intermolecular forces. So here we go. So there are two types of solids that we're going to discuss. Well, one type we're going to discuss, one we're going to mention right now. So a crystalline solid versus an amorphous solid. Crystalline solids are what we typically see or what we kind of know. Things are very well ordered. Every single one of these little spheres, little atoms in this is perfectly placed. Everything is in perfect position. There are these little holes here. There's the little, what we call interstitial holes here, and everything is kind of stacked absolutely perfectly, like you might see with a bunch of spheres. So if I stacked a bunch of golf balls on top of one another. And then there's an amorphous solid. An amorphous solid is still a solid, it's connected, but you'll notice that there are all sorts of little gaps. What we call is, so the crystalline solid is very ordered, and an amorphous solid is very disordered. Disorder is actually great when you're looking for flexibility, when you're looking for to have strength, less than a, so when you're looking at these two things, an amorphous solid, an example of an amorphous solid would be something like glass or plastic. Some types of plastics are. And then orders, this is going to be salt crystals or something like diamond. Actually, what I should really say is minerals, which are salts anyway, but crystalline solid, very well ordered. Amorphous solids like glass, they don't quite take on those characters. So yeah, crystalline solids are very hard and they're very perfect. Amorphous solids can have all sorts of different properties. So this again is an amorphous versus a crystalline solid. Again, perfectly ordered, as we can see here. And then these have all of these little gaps that are kind of not filled in perfectly. So again, we are going to talk mostly about crystalline solids. Amorphous solids, I just will say, are there, and they're actually really interesting when you get into material science, the idea of amorphous solids. And actually, we'll look at kind of all these different things a little bit later. So we have 4 different types of solids that we're going to talk about: ionic, metallic, covalent network, and molecular. So an individual unit of these bulk solid types. So a ionic substance has individual ions that make up essentially the units, individual units. Of course, it's going to be the interaction is, again, this is electrostatic, just like everything else. Because they're ionic, these electrostatic forces come in the form of alternating positive, negative ions. And of course, this goes in multiple dimensions. So positive, negative ions, it's just, that's the type of force that holds it together. The best example, and again, salts are the example that we're going to use here, are something like sodium chloride. Table salt is the perfect example of this. Basically, any metal and with a non-metal together is going to be the example of ionic. Okay, next up, metallic solids. Metallic solids are going to be individual units are metal ions. And this is a little bit different. Actually, I should not say ions, metal atoms. Okay, so these metal atoms are typically, they're not charged. At least the bulk material is not charged. Again, this is another electrostatic force. You have these positive metal atom nuclei. And you have these negative valence electrons. So these negative valence electrons, and ultimately what it kind of looks like is we have a bunch of these positive charges, and you have these electrons that are kind of floating all around between the two of them. The reason that these can conduct electricity is because it has these electrons that are kind of exchanging and they're kind of floating around. And the typical thing you hear is positive metal atoms in a sea of electrons. That sea of electrons is what allows the transfer of electrons, what allows conductivity. Okay, so yeah, so metal ions, again, held together by that glue of electrons. Again, those electrons just are anywhere they want to be. They don't belong to one specific thing. The example, I don't know, iron, basically just some bulk metal, iron, which is Fe, chromium, cobalt, take your pick. Any metal is example of a metal ion, but just that metal in its neutral form. Next up, covalent network. Similar to metallic, but they're going to be a little more restricted. So metallic was a bunch of these nuclei, the sea of electrons. And because it has that sea of electrons, it's very malleable and you can adjust it. Covalent network, on the other hand, is made up of individual atoms. Use green again. Use individual atoms. These individual atoms are actually held together by covalent bonds. Those covalent bonds are going to hold that together in a very stiff way. So what happens is you have these, instead of having, you have these atom centers that are going to hold together through a network of covalent bonds. So it's kind of this permanent arrangement of atoms that you end up with. These are in fact nuclei, but really what is going on is just those permanent bonds. The electrons exist here in the bonds. Just call those bonds. And those are the atoms. So again, it's just a network of those things. But overall, it's neutral. Covalent bonds, something like diamond or graphite is what we're going to see for this. And there we go. So that is the network solid. And there's two types, the covalent network, and then you could talk like an amorphous solid, which is covalent. So glass, more so like plastics and stuff. Those are amorphous solids that are considered network solids, but they're not. I mean, they're held together covalently, but they're not really, amorphous, not network, I guess I should say. Next up, molecular. So this one is, if I freeze water, I've got a bunch of molecules that are held together through intermolecular forces. So this is where the only place where intermolecular forces are going to come into play. And so something like ice is water held together by intermolecular forces. Sugar is a better solid example. So sugar molecules hold together because of the intermolecular forces that hold them together. These are probably have the lowest melting point out of all of these because the bonds are the weakest, right? Covalent bonds, very strong. Electrostatic forces, very strong. Metal bonds are actually probably the weakest of those bunch, but intermolecular forces are definitely weaker than all of those for the most part. So molecular solids, a bunch of molecules held together by those intermolecular forces. So here we go. So this right here is an ionic solid. Again, we have rotating negative and positive interactions. This right here are a bunch of different types of network solids. Again, these perfect arrangement held together by covalent bonds that hold these things together. Here we have an example of a metallic network or metallic bonding. Again, these are all positively charged, but there's electrons that are kind of holding them together in between all of these. Okay, so all of these are positive and we have kind of electrons that are floating all in here, holding these all together. Of course, this is always neutral. And then finally, this last one over here, this is going to be our molecular solids. Molecular solids, again, they're held together by intermolecular forces. These intermolecular forces kind of holding these things together. This can't really see it all that easily, but yeah, we've got intermolecular forces holding these together. This is layered, for example, but yeah, so we get these different molecular solids. Again, The individual units kind of give away what it is. We have 2 different ions in the first one. We have a bunch of covalent bonds in this next one. This is all the same, so it has to be metallic. And then finally, these molecular solids, which is molecules held together. So yeah, all right. So that is the different types of solids that we are going to discuss. Next up, it's important that we mention what an allotrope is. So this idea of allotropes are different types of network solids. So it is the same formula, but different configurations. So here I have diamond, right? So this is carbon in the diamond form. And going back to our shape discussion, we have a bunch of these tetrahedral carbons that are held together. And that is in fact what gives us, there it is, 1, 2, 3, 4 bonds. That is a tetrahedral carbon. That is what gives us the shape of diamond. Okay, it's all this tetrahedral shape versus looking at something like graphite, where you have these layers of, this is actually going to look something like benzene, just no hydrogens, but it's this network of just these sheets of graphite. So this is carbon as graphite. It's just sheet upon sheet of this graphene. If you've got, this is graphene, this is kind of all the rage for a while in material science, but you have a bunch of carbon molecules that are held together in this honeycomb-like network, and it just goes on repeated forever in just one 2-dimensional sheet. So if I put another sheet below this, it becomes graphite, right? So graphene, you stack a bunch of graphene on each other and you have graphite. In fact, how you make graphene is you take double-sided tape or tape, you attach it to graphene and you rip it off, and you have pulled off an entire layer of graphite. You now have graphene. And there are other types. So here we have a buckyball. A buckyball is C60 notoriously. This is kind of snaps together and gives you kind of this football shape, soccer, I guess, shape in the US. But we have, again, this is a 5-member ring connected to a 6-member ring, and there's a couple of 5-member rings there. You can look through it, but a buckyball is this completely spherical 60 carbon structure. We have carbon nanotubes, and again, stack sheets. This is graphene again, but all of these are different configurations, different allotropes of carbon, which is just different configurations. All right, crystal defects. So this is somewhat interesting. Crystal defects tell us a lot. Okay, so if you have a perfect configuration, so if we look at just this little section right here, it's a perfect configuration of whatever this, let's call it carbon, whatever this carbon happens to be. But you can substitute one of these atoms and put a different one in. So here we have substituted an impure atom, and it's about the same size. So we now have this section right here is going to have slightly different properties than my original one, because we have substituted some other atom about the same size in. So maybe we put a nitrogen in. If this is a carbon network, right? If these are all carbons and I put a nitrogen in instead, it's all of a sudden going to change the characteristics. And I'll show you in just a second why that is. Here's another substitution impurity with a larger molecule. And notice how it disrupts the shape and it disrupts the network, and that can have effects on its properties because it's going to change it a little bit. So this is going to behave differently than the other two. We also can put things in these little holes that we have. We call it an interstitial impurity. So we now have added some kind of other atom, and that little box is going to behave differently than the others. We can also delete an atom, and that one, because it has that vacancy, is now going to have different properties as well. So by changing crystal structures, by substituting, adding bigger, adding smaller, adding stuff that fits in between, removing them completely, we have completely different shapes. So interestingly, here are a bunch of synthetic diamonds. So you see the very first one, this is the original, everything is exactly where it should be. And this is what happens when you substitute a boron in. So you substituted a boron, which is about the same size as carbon, but this is a boron substitution. I guess substituted. Okay. Again, this is all carbon over here, but we've substituted some boron in. And over here, we've added, I guess you shouldn't say we added, we substituted in nitrogen. So this has 1 nitrogen, this has 2 nitrogen, this has 4 nitrogen, and the V is equal to void in a void. And what do you notice happens? Again, we're changing the behavior, changing the shapes of these things. Actually having nitrogen, in fact, the bottom here, you can see by changing the amount of nitrogen, again, same thing here, we're substituting in nitrogen and having voids, we change the color. So you change the characteristics of the crystal properties of it, or the network properties of it, by changing the atom, by adding in a void space, by changing it from boron, or by changing it to boron. Okay, if you look at your periodic table, you'll see it's lacking an electron that carbon had, which will change the color, okay, because you're going to get different absorptions and stuff. So very neat stuff when you're looking at this. From a material science point of view, this is very cool. You can say, all right, well, I'm going to just substitute in some nitrogen. I'm going to see what it's going to do. Or I'm going to try to knock out some of these and see what it's going to do. So very interesting stuff. In fact, the original kind of synthetic diamonds that they tried to sell, by the way, just quickly, synthetic diamonds are exactly the same as regular diamonds. So if you substitute in, they used to use a special seeding method that would make them all yellow because they added nitrogen in. That's what they had to do to seed the crystals. And so you get these special colors. So it's very neat that you can tweak these things through just some amount of chemistry. All right, good. So we'll move on to 10.6 in the next video, but this one is going to be a little bit more quantitative in nature.